So we've talked about pH a little bit with weak and strong, with weak acids and bases. Today we're going to talk about strong acids and bases and pH. But before we do that, we have to really get into a little bit more of what pH means and what it has to do with solutions. So obviously we can pause and write down everything on the screen at this point. Okay, so the first thing you have to understand is that every solution, every water sample, whether it's pure water, salt water, pond water, Pepsi, whatever the solution might be, has some hydronium and some hydroxide. And the reason for that is water molecules collide with each other and actually transfer a hydrogen, a proton, from one to the other. And that results in having water plus a proton, which would be hydronium, and then water minus a proton, which would be hydroxide. Now this happens at a very small rate. So like for every sample of water, you have like 500 million times more water molecules than you have hydronium ions, for example. And then of course the same would be true for hydroxide because they're 1-to-1. So it ends up giving you a molarity that's super small, 1 times 10 to the minus 7 molar. Okay. If we do a kW, kW is like Ka, and if you remember, Ka is just, or Kb, right, is just product concentration. So products over reactants, right? Well, we're talking, when we say kW, we're referring to this self-ionization of water equation, and my products are hydronium and hydroxide, and so they would go on the top. And then my reactants is just water, and that goes on the bottom. But since water is a liquid, it doesn't really have a molarity. So it just basically goes to 1. So your Kw, since water is neither an acid or a base, we don't call it Ka or Kb, we call it Kw, is just your two products, hydronium and hydroxide, multiplied together over 1. Because again, water would be on the bottom and water is not aqueous. So we already said that these two concentrations for pure water are both 1 times 10 to the minus 7. So if I multiply those two products together, I get 1 times 10 to the negative 14, and it's molar squared because it's molar times molar. Now, this never changes, and that's because if I add hydronium to pure water, hydroxide goes down proportionally, okay? So that keeps the Kw value, 1 times 10 to the negative 14, keeps it the same, keeps it constant. The reason for that is, let's say I add let's say I have a glass of water, and I add some glass of water, and I add some lemon juice, a tablespoon of lemon juice, okay? So it's going to make it yellow here, okay? So what we just did was we increased the concentration of hydronium because lemon juice is acidic, all right? But the result of that is to decrease the concentration of hydroxide. And the reason for that is because as we add more hydronium, that gives us more hydroniums to collide with hydroxide and cause the reverse reaction to happen. So by adding more of a product, it causes the reverse reaction to happen faster, and that's going to use up some of my hydroxide. So when hydronium goes up, hydroxide has to go down, and the two concentrations, the product of the two concentrations still gives me 10 to the negative 14 power. And the same, of course, would be true if we added something basic. If the hydroxide increased, the hydronium would increase proportionally. Okay, so let's get back to talking about strong acids. If we're calculating pH for strong acids and bases, let's start with acids. Strong acids ionize completely. And this is a list of 7 strong acids. These are the only strong acids that ionize 100%. You do want to write them down just for like homework problems and stuff, but you don't have to memorize these. I'll give you this list on the test when we get there. But all of these guys ionize completely. So like if you're writing an ionization equation for HCl, you don't have to write a two-way arrow. Okay, it's just going to be hydronium plus chloride, and it happens at a rate of 100%. And that's important because what that means is whatever molarity of HCl I use, let's say I have 0.005 molar HCl, that's going to result in the exact same molarity of hydronium. And that's going to allow me to find the pH very easily because of this because of this 1-to-1 ratio that always exists between the acid and the hydronium, and because it ionizes 100%. Okay, so let's look at an example. What's the pH of 0.0025 molar H2SO4? Okay, so the first step is going to be to write the ionization equation. So let's go ahead and pause and try that. Okay, so you should have written H2SO4 plus water yields hydronium and hydrogen sulfate. All right, so if we're looking for the pH, we know that pH is the negative log of hydronium. Well, I'm not directly given hydronium in this problem, but I am given the concentration of a strong acid. And because this is a 1-to-1 ratio and the ionization is complete, there's no Ka, there's no icebox problem that we have to do for this. It's just a 1-to-1 ratio. So what that means is, I mean, we could do the stoichiometry, but really all we're saying is the concentration of H2SO4 is equal to the concentration of hydronium. And again, that can only be said because H2SO4 is a strong acid. Okay? So therefore, if I want to know the pH, I can just take the negative log of 0.0025 to get my pH. So go ahead and do that and see what you get. Okay, so you should have ended up with 2.6 as your pH. Okay. All right, let's try another problem. How many grams of HNO3 are there in 750 milliliters of solution if the pH is 1.80? So it's another strong acid, which means that when it ionizes completely. And so it's a one-way arrow. So again, it means that whatever the concentration of the acid is will also be the concentration of the hydronium. We don't know what that is in this case, but we do know the pH. So what does pH give us if we think about our equations? We know that pH is the negative log of hydronium, but what if we're given the pH? What can I find from that? How would I find the hydronium from that? Okay, so we were also given this equation, right? 10 to the negative pH equals hydronium. All right. So go ahead and do that. Take 10 to the negative 1.80. See what you get. Okay. So 10 to the negative 1.80 should give us 0.01585. Okay. And that's the molarity of hydronium. But since this nitric acid is a strong acid, that means that it's also the molarity of the nitric acid. So think about this for a second. How am I going to get from molarity of nitric acid to grams of nitric acid if I know the volume? So in this one, we should start with the volume. So 750 milliliters of HNO3 solution. And we have to take it to liters. So milliliters of nitric acid to liters. So 1 over 1,000. Okay, and then from liters, if I'm trying to get to grams, hopefully you're thinking about what the next step would be, and that would be moles, right? And we know the moles per liter because we just figured it out, right? That was this number, right? So 0.01585 per 1 liter. And then from moles, I can go to grams. So moles of HNO3 to grams. So 1 mole of HNO3 is about 63 or 63.02, I believe. And so then that should give us our grams. All right, and it looks like that gives me 0.75 grams of nitric acid. All right. So let's look at bases then. Strong bases are all going to end in hydroxide. And essentially it's just most of the metals from the first two groups of the periodic table. So like lithium, sodium, and potassium are all in group 1, and then as well as rubidium, sorry. And then calcium, strontium, and barium are all in group 2. But these strong bases all just end in hydroxide, and they simply dissolve when they ionize. And we've already talked about this. So for example, if I had potassium hydroxide and it dissolved in water, it would give me K plus OH minus. Okay. And by the way, you don't have to memorize these either. These will always be provided for you. Okay, so let's take a look at an example problem. What's the pH of 0.000350 molar strontium hydroxide? Okay, so the first thing you're probably going to want to do is write the ionization equation. So strontium hydroxide breaks up in water to give us Sr2 plus 2OH minus. That's important because this is now a 1:2 ratio. For acids, it's always 1:1, but for bases, sometimes you have 2 or 3 hydroxides for every one of the base that you used. Okay, so if we're looking for pH, we're not going to be able to get that directly from hydronium for this problem because this is a base. It doesn't produce hydronium, it produces hydroxide. So the first step is going to be to see how much hydroxide we get from this reaction. So if I have, I'm going to change this to scientific here, 3.5 times 10 to the negative 4 moles of strontium hydroxide. The first thing I want to do is convert that to moles of hydroxide. Again, because I can't take it to hydronium because there's no hydronium in the balanced equation, but there is hydroxide. So I'm going to go ahead and say that there's 2 moles of hydroxide for every 1 mole of strontium hydroxide. Right, which means that I now have 7 times 10 to the negative 4 molar hydroxide. Just doubled it. Okay, so what can I get from this? I can't get pH, but I can get pOH. So the negative log of hydroxide is equal to pOH. So if I take the negative log of 7 times 10 to the negative 4, what do we get? Okay, so you should get 3.155, I'll say. Keep an extra sig fig there. But that equals not pH, but pOH. And then, if you remember, pH plus pOH equals 14. We talked about that last time. So if I do 14 minus pOH, that will give me pH, right? So you get 10.845. So 10.85. Oops. Or actually, I guess if I'm rounding to 3 sig figs, don't want to round twice. So just be 10.8. Which makes sense because this is a base, so it should make sense that we get a basic answer. Okay, so we're going to work on some additional problems and use these as a template, and you can obviously work together to try to figure some of them out, and I'll also leave the answers for you.